Hello everyone, I'm Li Fengzhou, a PhD student at Virginia Tech. Currently, I'm working with my advisor, Dr. Pratap Tokekar at the University of Maryland. Today, I'm going to talk about our TL paper on how to design sensor assignment algorithms to improve observability of underlying estimators when tracking multiple targets. We consider the problem of finding and assigning sensor subsets to track targets based on the observability performance. The observability captures how well the internal states of the targets can be inferred from the sensor's measurement. I will talk about the observability in detail later. Our objective is to improve the observability of target state estimators, such as Kalman filter or extended Kalman filter. As you can see from this example, each sensor can be assigned to at most one target, but multiple sensors can be assigned to track the same target. So this models N-to-1 assignment constraint. So this constraint is motivated by the scenarios where sensing multiple targets by the same sensor can be time-consuming or even impossible. For example, it takes the radio sensor 2 seconds to get a measurement for one specific frequency. So tracking multiple targets by the same sensor can be time-consuming. Also, if the sensor has a limited field of view or low processing capability, it's very difficult for a single sensor to track multiple targets. So we consider assigning a set of sensors to track each target. So in this way, we can reduce the task load of individual sensors for better tracking performance. So based on this constraint, we studied two versions of the assignment problem. The first one is called general assignment, where we assign sensor subsets to track targets. The size of each sensor subset can be different, and our objective is to maximize the summation of the observability measures omega from all L targets. Then we studied a restricted version of the general assignment problem, that is non-overlapping pair assignment, where we assign exactly a pair of sensors to track each target. This is motivated by the previous study that two sensors are necessary to track a target in a 2D environment if the sensor is either the range sensor or the bearing sensor. Again, the objective is to maximize the total observability measures of all targets. So these two problems are NP hard, which means there's no polynomial time algorithm for solving them optimally. And our study is different from the assignment problems in the literature from the perspective of the constraint and the objective. For example, some work has studied a one-to-one assignment, where each sensor or robot is assigned to exactly one task. And some work focus on one-to-n assignment, where each sensor or robot can perform multiple tasks. Well, our problem is the N-to-1 assignment, where we assign a set of sensors to each target. Also, the related work considers the linear objective, which is the sum of the individual objectives from all robots, where we consider a team objective, which may or may not be linear. So for solving the two versions of our assignment problem, we made three main contributions. First, we show some properties of various observability measures, such as monotonicity and some modularity. So for solving problem one, we show that a simple greedy algorithm can give half approximation for monotone and some modular objectives. And for problem two, we present a greedy assignment algorithm with 1 or 3 approximation performance for arbitrary observability measures. So I will first talk about the observability measures and then the assignment algorithms. Now let's see what is the observability in the target tracking scenario. We consider that each target has a single integrator motion model, while PTL is the target position and UTL is the target control input. This control input is unknown to the sensors. We assume that the sensors only know an upper bound of this control input. And each sensor measures the distance or the range to the target with some Gaussian noise, which means the sensors are noisy range sensors. And each sensor uses the extended Kalman filter to estimate the position of the target. So for the system of n sensors and one target, the observability matrix can be computed as the relative position between each sensor and the target. and the target control input. The relative position is known to the sensors, since each sensor can estimate the target position by EKF. So another part is the control input of the target, which is unknown to sensors. For this observability matrix, there are some measures on it, such as inverse condition number, the trees, rank, and log determinist. So for this observability measures, we care about two major properties. So the first one is the monotonicity, which means assigning more sensors to track the same target can improve the observability measure of the target. The second property is the submodularity, which denotes that assigning additional sensors to track the same target has the diminishing returns in increasing the value of the observability measure. So why do we care about these two properties? Because if the observability measure is monotone and submodular, there exists a very simple and efficient algorithm to optimize it. So let's see if these observability measures have these two properties. So we prove that the inverse condition number is neither monotone nor submodular. However, the trees and the rank of the symmetric observability matrix are submodular and monotone increasing. And its log determinist is submodular and monotone increasing if the symmetric matrix is non-singular. So for the observability measures that are submodular and monotone increasing, we study the problem 1, where we assign a set of sensors with a variable size to each target. So this problem is also called submodular welfare problem in the literature. And for monotone and submodular objectives, a greedy algorithm can give half approximation of the optimum. So what if the observability measure is not monotone nor submodular? For example, the inverse condition number. Then we study a restricted version, the problem 2, the non-overlapping pair assignment, where we assign exactly a pair of sensors to each target. So for solving this problem, we present a greedy pair assignment algorithm. It is very simple. At each round, it selects the sensor pair to track the target with the maximal value of the observability measure. Then we remove the selected sensor pair from the sensor set and remove the tracked target from the target set. We prove that it gives the 103 approximation of the optimal and runs in polynomial type. We also extended this result to the general case. That is, we assign exactly M sensors to each target, and our greedy assignment algorithm will give 1 over M plus 1 approximation performance. So to show its performance, we perform a simulation of the multi-target tracking. So here are 7 sensors plotted as the diamond are tasked to track 3 targets with the circular motion. So the target is plotted as the pentagram. The sensors use extended command filter to estimate the position of each target to get its mean position and variance. So here the solid square denotes the mean position of the target, and the ellipse denotes its variance. So you can see that the estimation error is very small for all 3 targets, which means the sensors estimators perform very well by using our greedy pair assignment. We also verify the approximation performance of our greedy pair assignment. Since our assignment problem is NP hard with the combinatorial complexity, so computing the optimal solution by exhaustive search takes a lot of time and is even impossible for a large number of sensors or large number of targets. So we relax the problem 2 and find an upper bound on the optimal value in polynomial type. And we compare the value of the observability measures, such as log determinist and inverse condition number, collected by our greedy pair assignment and the upper bound solution. And we can see that our greedy pair assignment performs very close to this upper bound solution and works much better than 103 approximation in practice. So in summary, we studied the monotonicity and the submodularity of various observability measures, and we present a greedy pair assignment algorithm that gives a 103 approximation performance for optimizing arbitrary observability measures. Okay, that's all about my presentation. If you have any questions, feel free to send me an email. Thank you.